Greetings, beautiful people. Welcome back to Find XYZ, where we think, find, and shine. Please, if you are new to this channel, kindly subscribe, hit the like button, and leave us a comment. Help me grow this channel. In today's episode, we are going to talk about another property of binary operation, which is commutativity. Let's look at this scenario. We are going to perform an operation which is mixing of colors. Now, in this case, we are going to select first a blue color, then secondly we are going to mix it with a yellow color. Now when we combine yellow and blue, you realize that what color did we pick first? We picked blue first plus yellow, and what is the result? We are arriving at green. Let's look at another scenario. Now in this case, what color are we selecting first? We are selecting yellow, then we are going to mix it with blue this time. So yellow plus blue, and when we mix it, what are we going to get? We are going to get green. What can you conclude from these two scenarios? The first one, we selected blue and added yellow. When we mix, we had green. The second one, we selected yellow first and add blue, and we arrived at green. The first case, we selected blue, then added yellow. When we mix, we had green. The second case, we selected yellow first, added blue, and then we had green. We can see that both cases we are getting green. This type of example is known as commutativity, which means that order does not matter. We don't care about the order in which we put things together. So whenever you perform an operation and the order does not matter, that type of operation is commutative property. There are some operations that when we perform, it doesn't matter the order in which we perform the operations, we are going to arrive at the same result. So let's define commutativity. Now we are saying that given an operator diamond, a binary operation is defined on a set S which contains an element A and B. Now if we perform A operation B, it should be equal to B operation A for all A and B in set S. Then we can say that operator diamond is commutative. The key thing you should note, the key thing is A operation B must be equal to B operation A. The order in which we perform the operations does not matter. Just like when you have an amount of money in both pockets, if you swap the amount of money in both pockets, you are going to get the same amount of money in your pocket. It will not change the amount of money. Swapping doesn't change the amount of money you have on you. So that is commutative. However, if swapping changes the amount of money you have on you, then you can say it is not commutative. Why is this useful? One thing you should take note is that commutative isn't just a rule that you have to memorize. It is a mathematical definition of freedom. Because we know when an operation is commutative, we have the freedom to operate on the given numbers whichever way order we want to operate them. So it gives us freedom. So if an operation is commutative, we have the freedom to arrange our work in whichever manner we want. But if it is not commutative, we are locked because we have to follow the order. Order matters. Let's take a look at our first example. A binary operation is defined on set P, that is X, Y, and Z, by the table below. Determine whether the operation is commutative. We have already defined commutativity as X operation Y must be equal to Y operation X. So let's verify some of the options. We can clearly see that X operation Y is giving us Y. Then what about Y operation X? Y operation X is also giving us Y. Then let's check the other options. So we can do X operation Z is giving us Z, and then Z operation X is also giving us Z. Then we can do Y operation Z is giving us X, and then Z operation Y is also giving us X. So we can clearly see that the operation is commutative by inspection. However, there's something that you should take note. Whenever you perform a binary operation and the operation is commutative, it will be symmetrical about the leading diagonal. Now let's look at the leading diagonal. Now this is the leading diagonal, X, Z, and Y. You can clearly see that the elements above is the same as the elements below it. Above and below the leading diagonal or the principal diagonal, they are the same. Whenever you observe this feature, you can also use this to conclude that it is commutative, aside relying on the rule where X operation Y will be the same as Y operation X. You can use the leading diagonal. Let's have a look at some examples. In a given example, an operation is defined on a set of real numbers where A star B is equal to A plus 2AB. We are to evaluate whether the operation is commutative or not using these expressions. So we are supposed to find 5 star 7 and 7 star 5 using our given rule. So let's start with 5 star 7. So 5 star 7, the rule says pick the first number. So we'll pick 5 plus twice of the product of the first and second number. So what is 5 times 7? That will give us 35. Then we have 5 plus what is 2 times 35? that will give us 70, and this will give us 75. Now let's perform the second expression, which is 7 star 5. The same way, pick the first number, which is 7, plus the product of the two numbers, which is 7 and 5. So we have 2 multiplying 7 times 5 will give us 35, which is 7 plus 70, which will give us 77. Now to show commutativity, we consider the order in which the operations were done. So we can clearly see that 77 is not equal to 75. So we can conclude that since 5 star 7 is not equal to 7 star 5, the operation star is not commutative. Let's try another example. We are asked to evaluate an operation on a set of real numbers that is defined as m. Operation n is m plus n minus 10 mn. We have to evaluate 2 operation 3 and then 3 operation 2, and then they are asking us what we can say about the results we are getting I and II. So let's start with I. We are asked to evaluate 2 operation 3. So we are always use the rule. So we have the first number plus the second number, so 2 plus 3 minus 10 multiplying 2 and 3. 2 plus 3 will result in 5 minus 10. 2 times 3 will give us 6. So we have 5 minus what is 10 times 6, that will give us 60. Then this will give us negative 55. Now let's perform the second operation, which is 3 operation 2, which is add the two numbers, then 10 and the product of the two numbers. 3 plus 2 will give us 5. 3 plus 2 will give us 5. Then minus 10. 3 times 2 will give us 6. Then 5 minus 60, which will result in negative 55. Now, what can we say about I and II? Clearly see that these two operations resulted in the same outcome. So since 2 operation 3 is equal to 3 operation 2, then the operation is commutative. So whenever you change the order or you swap the order in which you are performing the operation and it results in the same outcome, then you can conclude that it is commutative. It is commutative. Let's try another example. We have been given a binary operation which is defined on a set S, negative 2, 3, and 5, and we are asked to use this rule, which is A, B minus A plus B. Show whether or not operation star is commutative. Whenever you are given a finite set, you need to construct a table. So let's first construct our table. Now let's complete our table using the given elements. Now what is the rule? The rule says multiply the two numbers. So we'll do negative 2 times negative 2, which will give us positive 4. And then we'll do addition of the two numbers, which will give us negative 4. Positive 4, then negative 4 inside. Then you realize that there's another negative here, which will give us positive. That will give us 8. I will move quickly to complete the table, so take your time to verify the answers that I will show in the next slide. We have successfully completed the table. I hope you did same too at your end. Now let's see whether the operation is commutative. Now let's use the leading diagonal. Looking at the leading diagonal, let's look at the object below it and the object above. Are they the same? Yes, they are the same. Hence we can say that the operation is commutative. We can also use the definition where we know that A operation B must be equal to B operation A. So let's pick any of the two pairs. So we can do 3 operation negative 2. What are we going to get? Must be equal to negative 2 operation 3. So what is 3 operation negative 2? 3 operation negative 2 give us negative 7. Then let's look at negative 2 operation 3. That is also giving us negative 7. So we can clearly see that the operation is commutative. You can't use just one to verify. You have to verify all, because per the definition, everything must work. So it doesn't mean you only check for one. But with the leading diagonal, once you see that the objects above the diagonal and the objects below the diagonal are equal, then you can conclude that yes, the operation is commutative. One thing you should also take note is that whenever you ask to show whether an operation is commutative, when you are not given a finite set, you have to use the given rule to prove it. Don't use any numbers. Use the given rule with variables to prove the commutativity. Let's take a look at another example. In this example, we have to show the operation star is commutative. Now, what is commutativity? We say the order does not matter. So S star Y must be equal to Y star. What is X star Y? So X star Y is X plus Y plus XY. Then, so this is for this. Let's do Y star X. So pick the first letter. So Y plus X plus YX. Now let's rearrange it. Y plus X is the same as X plus Y. And then YX is the same as S times Y. So you can clearly see that S star Y is equal to Y star X. Hence, the operation star is commutative. One thing you should take note is that there are certain operators that they are commutative. So addition is commutative. Example, if I pick any two numbers. So a plus b must be equal to b plus a. So let's pick any two numbers. So I can do 2 plus 3 must be equal to 3 plus 2. 2 plus 3 will give us 5, and then 3 plus 2 also give us 5. So take note, anytime you have a binary operation that is defined on addition, clearly if it is just addition, you can see that addition is commutative, so you can conclude that it is commutative. Then multiplication, so a times b must be the same as b times a. The order does not matter when you are performing an multiplication operation. So let's pick any two numbers. So 5 times 6 must be equal to 6 times 5. Now what is 5 times 6? 30. What is 6 times 5? That is also 30. However, division and subtraction are not commutative. Why am I saying so? Let's pick any two numbers. So let's pick 3 and 5. So 3 divided by 5 is not equal to 5 divided by 3. Because 3 over 5, is it the same as 5 over 3? Nope, they are not the same. Also, 3 minus 5, is it the same as 5 minus 3? What is 3 minus 5? Negative 2. Is it equal to positive 2? Clearly, these two are not equal. Hence, division and subtraction not commutative. Thank you for joining me in today's section. Don't forget to subscribe, leave a comment, and see you in the next video where we discuss another type of property of binary operation. I'm out.